ja mam na imię Sebastian. Ja studiuję na University of Sheffield UK. Jestem tu już od ponad 7 lat. Zrobiłem tutaj undergraduate w Computer Science and Artificial Intelligence, a potem stwierdziłem, że jeszcze nie jestem gotowy odejść z uczelni i zacząłem doktorat w Speech and Language Technology, CDT, co jest takim jakby, to jest taki program, w którym ludzie dołączają jako kohorta, jako taka grupa i robią doktorat razem. I właśnie jestem teraz w ostatnim roku, będę kończył za pół roku. Mój doktorat jest na temat używania kontekstu w tłumaczeniu maszynowym. I tak, dzisiaj chciałem pogadać trochę na temat mojej najnowszej pracy. Jest to publikacja, która jest obecnie under review, więc i w sumie pierwszy raz o niej mówię, więc jestem podekscytowany. Wykład będzie po angielsku i tak, to dobra, to zaczynam. This is joint work with Robert Flynn, who's my colleague from the CDT, and Carolina Scarton, who's my supervisor. The paper is called MTCue, Learning Zero-Shot Control of Extra-Textual Attributes by Leveraging Unstructured Context in Neural-Machine Translation. Let's first talk about what neural-machine translation is. So walking sort of backwards in the name, we have translation. So translation is a transfer of meaning and function from one language to another. Machine translation is the act of automatic translation. And neural machine translation is machine translation implemented with neural networks. Simple enough. Nowadays, neural machine translation typically involves an encoder-decoder architecture. So this is kind of like an architecture where the input, the source sentence, is passed with an encoder, which creates a representation of the input that is then used by the decoder to decode the translation hypothesis. So you might ask yourself, no, I will for sure, because that's my thesis. What about context? So we know that, when you translate a sentence from source language to target language, and you just use the contents of the source sentence, that's usually not enough, right? So to illustrate, I have a few examples. So first example, we have a king on a throne. So in this case, let's treat that the context is an image. In my work, the context is usually text, but it could be image. So we have the context of a king on a throne, and the English sentence is "I'm finished." So the king looks quite concerned. So if I was translating it to Polish, I would translate it as something like "Jestem skończony." But if it was a school child, this translation doesn't make sense, right? Because if a school child says "I'm finished," that probably means that they finished their exam or the homework or something. So the better translation would be "skończyłem." But obviously, without the context, we aren't able to choose between the two and know which one is correct. So another example, we have two people in a kitchen, and one of them says "they're done." So again, in a kitchen setting, "they're done" probably means we're talking about, I don't know, cookies or some sort of food that has just cooked. For example, we can translate that as "już się upiekły." Well, if we have another king here who's also on a throne and he looks quite angry, if a king like that says "they're done," it probably doesn't mean that about cookies. It probably means that about, I don't know, some subject that he's very angry at. So he'd probably say something like "są skończeni." Again, without context, we're unable to say which translation is the right one. So context matters. So I keep talking about context, but what does context actually constitute of? So in my work, I split that into context that's found within the text that we're dealing with and outside of the text. So within text, that's quite obvious. So if we're dealing with dialogue, that will be previous utterances and future utterances. If we're dealing with an article, that will be previous paragraphs or the current paragraph that we're dealing with, etc. Now, outside text, that's a bit more nuanced. So we have things like gender, so the gender of the speaker or the gender of the person we're talking to. We have the formality of the exchange. We have the number of addressees, so whether we're talking to one person, a group of people. And then we have things like, these are all examples. It's not like a finite closed set. We have the age of the speaker, which, children talk differently than to adults, kind of thing. Then we have, for some domains, we have some extra contexts, such as for films and TV shows, we have the plots of movies or TV shows. We have the authors of the script. That might seem a bit weird, but it matters because people have, so the writers have their own specific style, and so it's worth, perhaps that context actually does have meaning in some examples where that a certain writer uses a certain phrase a lot, etc. And then current year, so this is just to signify that speech of the 1920s is different from speech of the 2020s, etc. Right. So now we know what context is. How can it affect translation? So I usually classify it as two things. So either a grammatical effect and a behavioral effect. So a grammatical effect is when the context that we have has a very explicit impact on the sentence. So, it's very easy to explain to an audience of Polish speakers when we're talking, depending on whether we're talking to a man or a woman or a group of people or one person, or formally or informally, we will use different morphology in our sentence. So in the top example, we have byłem studentem, gdy państwo uczyliście. So that's, from that sentence, we can infer that it's a man speaking to a group of people formally, whereas from the other sentence, byłam studentką, gdy uczyłaś, we can say that that's a woman speaking to one person informally. Now, as you can see, you can infer the context from the sentence, and also you can infer the translation from the context. So if you were given the source sentence, I was a student when you taught, and a context, a man speaking to a group of people formally, you would be able to translate it correctly, right? And then vice versa, if you were given the source sentence and the translation, you would be able to infer the context. So that's kind of like a property of grammatical effect. And contrast that with a behavioral effect, where that's kind of more nuanced, and we're talking about phrases and expressions that are more likely to occur in a specific context, but they don't have to, right? So this example, we have the English sentence, "You're a dimwit," and I ran it through Google Translate, I think, and I got the translation "jesteś głupcem," which you can back translate as "you're a fool," and that's an okay translation. But the context of the exchange I was translating was two kids in a cartoon talking about doing the homework. So if you have two kids speaking, kids won't say "jesteś głupcem," right? They will say "jesteś głupkiem" or "jesteś głupi." Obviously, the machine translation system doesn't know that we're talking about kids, that the kids are talking. So the reference translation and sort of an example of a good translation is "jesteś głupkiem." But if you contrast this with the grammatical effect, there's no rule saying we have to use one or the other word, right? It's just about what's more likely in a given context, what's sort of more typical in this particular social situation. So yeah, we're just talking about adapting our language to a given situation rather than about how context grammatically impacts the sentences. Cool. So now that we know what context is and how it affects translation, we need to ask ourselves, how can we capture this effect in machine translation? So we need to talk about the challenges. So challenge number one is that, you would want to work with data that's well annotated and that has an entry for every field that you want. But in practice, when I work with contextual data, there's often gaps. There's often fields which will have, there's often fields like, I don't know, just character description is a common one, where it's only available for some characters. And that's less than ideal, because let's take a look at the example. We have two samples. Sample one, this corresponds to the example with the school kid and the king, and they both have some contexts available for them, but as you can see, none of them overlap. So we have gender for only one of them, we have age for only one of them, we have description for only one of them, etc. So if you were to say, okay, I think actually to simplify this problem, I'm going to skip all of the context and just focus on the description, because it's the most descriptive context. It kind of makes sense. I should be able to infer all the information I need from description. Well, description isn't available for some of the samples. So if you were to use the description, in this case, you wouldn't be able to leverage sample one in training or in inference. So that's not helpful. But if you take a look again at the context, then you can see things like, okay, well, we have a teenager and we know that the location is school. Is that enough to say that "am finished" should be translated as skończyłem more often than as "jestem skończony"? Probably yes. I mean, I can't imagine a teenager saying "jestem skończony" unless, in a comical sort of cartoon scenario. And then likewise, if we look at the king, we have male, a tyrant king struggling to maintain his kingdom, political drama, audiences with the king. Well, that also kind of suggests that the more likely translation for this scenario is "jestem skończony". So even though we haven't looked at any particular field, we were able to sort of paint the picture with the available context. So the information is there, it's just not there. We just need to know how to use it. So as people, we're intelligent and we are able to make inferences based on the information that we have, and that's kind of what we want for the system. Now, another interesting thing that I want to highlight here is that there are correlations in this data, and in fact, correlations are very typical in context data in general. By correlations, I mean certain context variables are likely to occur together more often than not. So like teenager in school will occur more often together than adult in school, or male and king will occur more often than female and king, because female king is a queen, etc. And then also some of the information contained in some contexts is already contained in other contexts, which means that some of it is redundant, which we don't really care about that much. But that's just to say, it's most of the time it's okay that we're missing some information, because already with the information that we do have, we're able to sort of paint a picture that's sufficient for translation. Cool. So challenge number 2, context comes in various shapes and forms. So we already know that context doesn't always come, but when it does come, it comes in formats that are not very friendly to parse or use in translation in training neural models. So we have stuff like gender, that's categorical. Even if there's more than 2 categories, that's still categorical. Number of addresses, we have singular or plural. Formality, at least 2 stages, formal and informal. Some languages have more, like Japanese, I think, has 3 or more. Previous sentence is textual, it's not categorical. It will always be different, and it sort of as an interesting property, it has roughly the length of the source, and that's just to say it sometimes will be short, like in dialogue, which I work with mostly. These are very short, but like in some domains like articles, they will be quite long. Plot descriptions, textual, long, usually more than 2 or 3 sentences. Character description, again, same as plot description. Pardon me. Profession, that's textual in my opinion. You could say that it's categorical, because there's a finite number of professions in the world. But in practice, when you work with this data, we have a data set of professions for 800 plus speakers, and almost all of them are unique, and that's just because there's different professions in the world, and also some people have two professions, etc. So treating it as a categorical variable is not very helpful. So that's why I treat it as a textual variable. And finally, age bracket, it's categorical, but it's fluid, right? So unlike with number of addressees, which is singular or plural, or with age, from dataset to dataset, you can have different categories. So you can have one dataset that uses numbers, so just how old someone is. Then other datasets can have categories like generations. So are you Gen Z, are you millennial, etc. You can have decades. Are you from the 50s, 60s? And in our case, we use a bracket of sort of teenager, young adult, or elderly, etc. So even though it's categorical, thinking of it as categorical is unhelpful because categories can be different from dataset to dataset. There's no standardized way of thinking about this. Cool. So to summarize all of this so far, context is unstructured and underrepresented. Context information can correlate. Context can come in various formats and quantities. So what would a good framework for context do? A good framework for context in translation, obviously, treats context as a whole rather than each variable individually. Okay? Because we know that if we treat variables individually, when we don't have the data, that will be a problem. When we treat it as a whole, there's always something. There's always something else we can go by. Uses what is available to fill the gaps. That's kind of the same point as the one before, but expressed differently, I suppose. We have some of the context information. As we know, there's redundancies in them. So we know that if we have some of it, then that will kind of fill the gaps of what is not there, which, yeah, kind of the point as before. But also, if our framework does this, then it reduces the need for expensive manual annotation campaigns because, sometimes people have a data set with holes, and the first thing they think about is, okay, let's have a campaign and just fill in all the gaps. Well, perhaps we don't need to do that, which, it is massive if we don't need to do that because there's a lot of data that's already there, but people often don't use it because they don't know how. So that was also kind of one of the assumptions of this project, was to use what we have. And finally, scales the number of context variables, and with the idea that more contexts mean a fuller picture of presented reality. So that is to say, if we have just the film data, then we're able to talk about the general theme of the scenario, right? But if we also have speaker data, then we also know a lot more about the person that's saying the utterance. And so, for example, it's kind of tricky to say anything about gender or formality by just knowing information about the film. So the more context we have, or the more types of context we have, the better the picture of the reality that the translation needs to occur in, and therefore the more informed and better the translation will be. Cool. So let's talk now about the approach that we built. So we called it MTCue, which is short for machine translation with contextual universal embeddings. And yeah, so how have we solved all of these challenges? Well, first of all, we decided to focus on the challenge of all the contexts having different shapes and forms. So how do we handle that? Well, first, we decided to sort of ditch categorical data and rewrite all of the categorical data as text. I say descriptive text. That is to say, I'm not rewriting singular, plural as a sentence that says 1, 2, right? I'm rewriting it as I am talking to one person, or I am talking to a group of people, which is exactly what the example says. And then second, we define a vectorization function, which takes all of this text and then maps it to vectors, right? So this is a lot to wrap your head around. So this example shows a script. It's just like I made it up, but it's got some metadata. It's got a title, it's got a year, it's got an author, it's got location, etc. Great. So we take all of this text and we tokenize it. So we convert the words to tokens, and then we will want to create embeddings of each of these context variables. But obviously, an embedding, if we just embed word by word, then an embedding of the description, like Andrew, a middle-aged dad, blah blah blah, that will be very long, and the embedding of 2006 will be very short. Whereas we don't want that, because we are kind of working under the assumption that all of these contexts are like equally useful. Therefore, we want them to be equally sized. That also helps with just parsing them in general. So we're tokenizing them. Then we're using a vectorization function, which is a sentence embedding model. Now, I don't know how many of you are sort of familiar with them, but sentence embedding models basically embed sentences into vectors. So any sentence that you have of any length, which is crucial for us, is embedded into a vector of x dimension. In our case, it's 380 something, 384. So all of these different length texts will be embedded into vectors of 384 units, and then we just kind of concatenate them together. So the final representation that we have is sort of a vector, sorry, a matrix of in this case 1, 2, 3, 4, 5, 6, 7 or 8 contexts, and they're all of the same size, and they're all nicely packed into one matrix. Yeah, so that's how we handle them. One more thing that I need to mention about sentence embedding models: why do we use them? We don't just use them because they make the vectors of equal size. We use them because they are trained with a cosine similarity objective, which means when they produce these embeddings, the embeddings aren't just random numbers. The embeddings are meant to be two embeddings that are more semantically similar will have a bigger so we'll have a smaller cosine distance, right? So the idea is you create embeddings that kind of, if you visualize them on a space, the closer together they are, the more semantically related they are. Okay. Cool. So second thing is, how do we incorporate context in the encoder-decoder architecture? So the architecture I showed you at the start, that doesn't really lend itself to including extra inputs, because it's kind of, it's got one encoder, one decoder, and that's it. So what we do is we add an extra context encoder. So the context vectors that I talked about before, we use them as inputs in the context encoder. And then that's kind of in parallel with the source encoder. Then we combine them, the outputs of the both encoders somehow. I'll get to that soon. And then that just goes to the decoder, and everything else is as normal. So we just have one extra encoder, and the information is kind of put together. Cool. So, so this is what the architecture looks like. It's very, very complex, but it actually isn't. So this, the styling of this figure is taken from the original transformer paper. The architecture is based on an off-the-shelf transformer model, but we add a context encoder on the left, and we add a context source combination method, or should I say methods, because we don't really know which one is going to be best. We came up with a few, so we tested all of them, and I'm not going to go through all of them. I'll just go through 2 of them. But let's go. Let's sort of unpack this picture. So context encoder looks like this. So if we look at the figure, we have at the bottom, we have document inputs and metadata inputs. So in our experiments, we used both within text context and both outside text context. So we metadata that we had access to, like plot descriptions, PG rating, etc. And then we also used document inputs like previous sentences. So we put them together. And the reason I'm separating them on this figure is because I embed each previous sentence separately, but then we kind of hypothesized that you also, if you do this, you also need some sort of information in the model about how far away this particular sentence is from the current sentence, right? Because if you just embedded them all, then you're kind of treating them equally. Whereas in fact, the previous sentence, for example, the immediate previous sentence is way more useful than like the sentence 5 sentences ago. So we just use a simple positional encoding to add to the document inputs, but then we just concatenate them together and treat them the same from then on. So yeah, so the inputs are vectors, and the markers are used. The markers are the positional encodings, and then the encoder looks just like the source encoder in a normal transformer. So other than that, it's just really a simple component. The source encoder, I mean, I'm not going to talk about this because it's just the classic source encoder from the transformer architecture. The decoder is also the classic decoder from the transformer architecture, but we can't just, in a normal transformer, there is sort of an encoder-decoder attention component, which takes the outputs of the source encoder and combines them with the decoder hidden state, and then it goes forward. But here, obviously, we have two kinds of inputs. So we decided to figure out which is the best strategy for combining these two inputs. Now, obviously, we're not the first people to try this, so we were working with a lot of previous work. So these are the 5 sort of approaches that we came up with. So I'm not going to go through all of them, but they all have the same idea: how to combine the outputs of 2 encoders together so that the decoder can leverage them the best and produce the best translations. That's the idea, really. So I'll go through 2 of them. So I'll go through parallel attention, which is basically compute context target attention as in the normal transformer, compute source target attention as in the normal transformer, and then add both position-wise. Right, so the two matrices that are the result of these operations, they will have the same shape, so you can just add their values, and it's fine and it works well. Then flat attention is even simpler. You just take the feature vectors that are the outputs of the context encoder and the source encoder, you concatenate them together, and then you do the decoder attention on that. So even simpler. But these are the types of things that we do in this massive brown box. Cool. So results. So we ran the experiments using open subtitles. It's a corpus of film and TV subtitles with IMDb attributions, which means for any sentence, you're able to trace it back to a particular film or TV show, which we did, and we extracted some metadata with an Open Movie Database API. And the metadata we extracted were plot, genre, year of release, country of release, writers, and PG rating. We worked with 3 language pairs in both directions, so English to and from Polish, French, and German. As evaluation metrics, we used Blue and Comet, and the results we got were pretty good. So MTCue was better than the baseline model, a non-contextual transformer, by 1.93 Blue and 3.72 Comet on average. Perhaps an interesting observation was that the biggest improvement was for English to French, smallest for German to English, but in general, the biggest improvement was for language pairs from English, not into English. So all the pairs like English to French, English to Polish, English to German had massive improvements, and the pairs into English, not so much. They still had improvements, but they were not as big, which kind of makes sense because English as a language does not render that many contextual phenomena. So again, going back to the example of gender and formality, etc. English doesn't have any of that, and Polish has all of that, and similarly German and French. So even these phenomena, they don't really get rendered in English. So you don't get that benefit by including context when you translate into English. And then for combination methods, parallel outperformed other combination methods, but by a slight margin. They all worked just as well, to be honest, and it's very possible that on another data set, another method would have been better. So it doesn't really matter which one you use. Cool. So now on to the more interesting results. Serious shot control of formality. So in the data set that we used, open subtitles, no samples in training data were annotated with formality type. So they only had plot descriptions, etc. Nevertheless, when I first played with the model, I started giving it some things to some examples to try. So we've got a source sentence like, I got 100 calls in your city, and I just said, okay, as context is just one context, and I wrote a low rank official speaking to a high rank official, and the hypothesis was formal. And then I tried what's up fam, and the hypothesis was informal. So that seemed like an interesting and non-random result. So then I tried to sort of take it a step further and look at a bigger scale. So I ran a little evaluation on the test set that I had access to, which given some hypotheses is telling you what the proportion is in them of formal and informal translations. And it turned out that the model, for some contexts that seem formal, like low rank official speaking to a high rank official, the model was producing overwhelmingly formal translations, and then likewise for informal. So we did a little experiment. So we sampled 800 unique context inputs, like countries, genres, previous sentences, from 2 data sets, so from open subtitles, the one we worked with, and from an in-house data set, also of a similar domain, also films and shows, but a different data set. And then we ran a formality evaluation, the one I said, where given a context, the model produces 600 hypotheses, and then a scoring script gives you a formal-informal ratio. So for example, 35%, 65%. Cool. So this is what happened. So I decided to visualize all of the contexts that we used using UMAP, which is kind of like a visualization software for embeddings. So on the left, we have the inputs of the context encoder. So these are the MiniLM v2 embeddings. MiniLM is the model we used for context embeddings. And as you can see, I should also explain that the color scale in here is the formality. So the lighter the shade of green, the more formal the translations are for this particular context. The darker the shade of green, the more informal they are. If it's somewhere between light and dark, then it's kind of mixed. As you can see on the left, we kind of have little groups of embeddings, which is not surprising because some contexts like PG ratings will look very similarly, so they will be one clump. And then the biggest clump is probably the previous sentences, etc. And then the circles are the in-domain context, so open subtitles. The X's are the other data set. And so yeah, so if you look at the at plot B first, you can see that there is a pretty nice regularity to these embeddings, right? If you look at what embeddings are light green, they are all in kind of their own areas, and then likewise the dark green are in their own areas, which means that the model kind of learns a representation of context that is kind of ordered to make translations with specific in this case with specific formalities possible. So if we just wrote a context and embedded it and visualized it on this plot, we would know that okay, if our new context landed somewhere in the dark area, that context is going to produce an informal translation, and then if it landed in the light area, it would produce a formal translation. which is a pretty nice result because it means that MTCue learns a representation of context that is ordered for some other context phenomena that we haven't really trained it on. And yeah, hope that makes sense. So if you sample from this embedding space some informal context, the context that produce informal translations, a sentences like "What's wrong with you?" and "What's he doing now?" and also sentences with colloquial expressions, whereas formal contexts, so contexts that produce formal translations, are things like, "Then why are you still in my office?" And "I can see you're very interested." And also sentences with full names overwhelmingly produce formal translations. So obviously, English is not a formal/informal language. In English, it's more formality is expressed through word choice. And as you can see here, it's very well sort of mirrored in these contexts, right? So "Then why are you still in my office?" is something that you would probably say in a formal setting. "What's wrong with you?" is something that you would say in an informal setting. So the model learns to understand which contexts occur more often in which situations, which is exactly what we wanted. Cool. So a final result that I'll just talk about very quickly is we also tried a multi-attribute control scenario where we have that's sort of from my past work, which is the work that I was actually presenting when I met Maciej. So we are in that task. We are interested in producing translations into Polish, which, given the gender of the speaker, the gender of the interlocutor, the number of addressees, and the formality, which agree to all of these contexts. So in our paper, we were able to achieve over 99% accuracy with just supervised data and simple tagging approaches. So I wanted to see how well MTCue would do on this if we pre-trained it on open subtitles and the sort of film metadata. And so how it would do zero shot without any fine-tuning, and then how it would do if I fine-tune it on more and more data. So here's what happens. I compared it to a tagging baseline, which is the model from the original paper. So zero shot, MTCue achieves 80% accuracy, which is great compared to 67 baseline. And then with just 100 supervised samples, MTCue goes up to 90% accuracy. And finally, with full supervised data, it has over 99% accuracy. Now, there's an area where between 10 to the power of 3 and 10 to the power of 5, where tagging outperforms MTCue, which is an interesting finding, which we think happens because MTCue is kind of relying a lot on the context prior from the metadata, from the film metadata, and then as you train the models on more and more data that's actually annotated with the right gender and formality labels, etc., the tagging model without any prior is able to learn from that data set more easily. But finally, when all of the data is annotated with the gender, etc., attributes, MTCue gets to a good accuracy. And then blue is a lot better for MTCue with few samples, and then with a lot of samples, it kind of coasts around the same as tagging, which also confirms that MTCue isn't producing bad translations. It's just relying on another idea of context because it was pre-trained on different data. Cool. So I had to kind of rush through the last bit. I hope it made at least a little bit of sense, and hopefully you can still ask me a question. So, but the conclusions for this presentation are that context is useful, and it also is useful in theory and in practice. MTCue, the model we proposed, can learn a general idea of context and use it to improve translations. And this idea helps guide zero and few shot controllable translation. Cool. So future work, something we're working on now, is releasing Cornell Rich, which is a richly annotated corpus of English film dialogue. So we've collected data such as speaker characteristics, character descriptions, characteristic quotes, etc., and then also film metadata. And we'll release that soon. I think we'll release it at the end of March. And then finally, more work in this area could generally be about data collection to make, the more context you have, as I said, the better. And with the recent release of ChatGPT, we kind of toyed with this idea. We didn't go with it, but ChatGPT creates really good data sets. If you have someone if you have a team to sort of verify everything that it's created and make sure that it's true, then for domains like film and TV, it's a great tool. But obviously, it's very early to say whether it's actually a great tool. But that's something we thought about. Cool. So thank you very much. I hope this made sense, at least a little bit. This is my email. If you have questions, then you can email me.